All right, thanks, Tom. Our next presentation is Andy Ryan, EMILIA-3D, Advanced Thermal Imaging of the Lunar Surface.
All right. Hello, everyone. So I'm going to be talking about EMILIA-3D, which is the emission imager for lunar infrared analysis in 3D. I'm the PI of this proposal that's ongoing right now. I'm a research scientist in the Lunar and Planetary Laboratory. So I'm going to set the stage a little bit. So this is a fairly recent image taken by the Blue Ghost lander from Firefly Aerospace. This is one of our first images of the lunar sunset on the surface of the moon. And this is an environment of extremes, as many people in the room know. The illuminated areas can be up to almost 100 degrees Celsius, and then maybe just a few meters away in shadow, you can have minus 150 degrees Celsius. But we can take advantage of this. One of my favorite quick history lessons here is almost 100 years ago, astronomers at Mount Wilson Observatory observed the surface of the moon with thermocouples and measured a lunar eclipse and measured how temperature changed as the shadow of the Earth passed over the surface of the moon. They were able to use these temperatures to make some inferences, which I've highlighted at the bottom of this conference abstract from 1928, where they determined that the lunar surface is covered in a fine powder. And this is decades before this was confirmed by any surface lander. So this just illustrates the power of thermal observations for planetary science. And you can learn a lot more than just, is it a powder or is it a rock? I won't go into great detail here, but this is the backing motivation for sending thermal imagers to numerous planetary surfaces or orbit, including Mars, asteroids, Europa, and so on. So temperatures on the surface of the moon are not just dominated by the material properties, which is what we're really trying to get after. They're also dominated by the topography. So this is a little thermal model that I ran for a simulated meter square patch of terrain right before sunset. And you can see that you have these really extreme temperature variations where the shadowed areas are minus 140, the illuminated areas are plus 70 Celsius. And what you see depends a lot on the direction that you're observing it. Where if you're standing with the sun at your back, you see a lot of warm surfaces as shown in the frame in the bottom left. From the side, it's kind of in between. And then if you are looking towards the sunset, like in the bottom right, you see a much cooler terrain. And orbital assets don't see this type of topography. And so they're just seeing different temperatures depending on the direction that they're observing the surface. And so this is one of the things that we want to study in situ with our instrument. So we are proposing the emission imager for lunar infrared analysis in 3D, EMILIA-3D. This is a camera suite on top of a robotic gimbal that allows pointing. This is targeted currently for a stationary lunar lander and consists of an uncooled thermal infrared imager and a stereo pair of visible cameras. So the thermal camera is in the middle, and we have two visible cameras on either side. The idea here is that we are able to collect thermal image temperature maps of the surface and simultaneously create three-dimensional DTM reconstructions of the surface. So we get topography and temperature at the same time. We understand the instantaneous illumination conditions that so strongly influence the surface temperatures so that we can do a better job of extracting the material properties of the regolith. So that's kind of our tagline in the bottom there. This is the first time that a coincident observation like this, where you have an integrated suite, would be proposed for a planetary surface mission. And so our current opportunity that we're targeting right now is for deployment as a part of one of the commercial lunar payload services or CLIPS landers. There's a current call right now that we're proposing for a standalone instrument that is site agnostic. And so we are proposing to send EMILIA-3D on a stationary lander that would observe the lunar surface throughout a single lunar day all the way up until sunset. We can accomplish our science objectives, which I'll talk about in the next slide, basically anywhere on the moon, and complete them without any complementary payloads of any kind. So the idea is we would be mounted on the top deck or on the side of a stationary lander. And with a single axis or a two-axis motion control system, a gimbal system, we'd be able to observe different portions of the terrain within the immediate vicinity of the lander, which may have been influenced by the thrusters that would scour and remove some regolith within about 5 meters of the lander out beyond that scoured terrain to look at some pristine regolith surfaces. So our science objectives are first and foremost to do an in situ characterization of regolith thermal and physical properties. This has been done quite a bit from orbit, but this would be a ground truthing of those observations. Regolith physical properties tell us about the story of regolith production. This is the breakdown of rocks by meteorite impacts, the fusion of particles by other impacts, the continued breakdown by even smaller micrometeoroids, space weathering by cosmic rays, etc. Layering of material by impact ejecta deposition, excuse me. As I spoke about a few slides back, we want to understand this phenomenon where you see different temperatures when you observe from different directions, known as the emission phase function. My numbers got out of order there. We want to study polar-like thermal environments, even if we're not going to the poles. We can do this when the sun has just risen or is just about to set, when you have a lot of shadows covering the lunar landscape. We'll be able to do a better job of understanding how fast and how cold those shadowed areas get, how fast they cool, and what are the absolute temperatures they reach, which has pretty important implications for the volatile mobility and deposition processes on the moon. These small shadowed areas that are only a meter in size, they could actually trap volatiles that are on their way to the South Pole, migrating to a more permanent storage position. And so it actually could inhibit, in a way, the development of large water ice reservoirs in the lunar poles. And so we want to understand this process a little bit better. And we want to understand how exploration affects the surface. That scour zone that we're going to produce could drastically alter the thermal and physical properties of the regolith. If a lander, for example, were to land in a shadowed area where there's water ice buried beneath the surface, we'd like to know if we are destabilizing that ice by compacting or brushing away regolith so that it would sublimate away in human timescales, and we might be in a little bit of trouble. So understanding those types of phenomena, even if we're not going to that area, we'll be able to learn a lot anywhere on the moon. I think with this suite of instruments, the combined thermal and stereo pair of visible cameras, we have a lot of future opportunities developed to us. So we're going to be on the lookout for other future calls, and we're always open. Come talk to me if you have ideas. I could see a place for this instrument for rover autonomous navigation and surface science. So this could be on a robotic rover used to create terrain models while also measuring temperature for science and also for operational constraints. This could eventually be designed as an astronaut handheld tool to, again, examine regolith properties for science, but also navigability, like understanding the geotechnical properties of the surface, identifying zones with possible water ice, and also aiding in the deployment of other scientific instrument suites. I was recently working with Angela on the thermal design for the LEMS instrument, the seismometers that she spoke on. And we were trying to predict what would be the temperature at the South Pole. Well, they don't know exactly where they're going to go yet, so it's kind of anywhere in the South Pole. And well, it turns out if you are on a surface that's tilted towards the sun by 5 degrees versus tilted away from the sun by 5 degrees, you can have a temperature difference of 50 degrees, which can make or break your deployment. And I would not expect an astronaut with a big helmet walking around on the surface to be able to look down and say, yeah, that's tilted 5 degrees towards the sun. I'm pretty sure. So this is the type of instrument that could help them make those evaluations. And even beyond the moon, I think that we have a lot of opportunities ahead of us for other planetary bodies such as Mars, asteroids, outer solar system moons, and so on. So these are my summary slides, but I'll just leave them up there and take questions. Thank you. Down to silence.
Okay,
Thanks.
thanks again.